support assignment number 12. It was this one, all about probability. It's a really lovely question. I'm going to take my time over it. But yeah, let's get straight into it. So you're selling raffle tickets, £1 ticket. In the queue, there are M people with £1 coins and N people with £2 coins. Now, raffle tickets cost £1, which means if someone turns up with a £2 coin, you need to have £1 ready to give them as change, but you have no coins to start with, right? So what this means is that if a person with £2 arrives first, if they're the first person in the queue, and any arrangement of people is equally likely, if the first person to arrive is someone with a £2 coin, you can't serve them. But the moment you do have someone with a £1 coin coming in, then you have that person's pound to then give to this person as change, right? So if you make a little probability tree here, if the person with £2 turns up first, which is probability 1 over n plus 1. Now, the reason it's this probability is because there's one person with £2, in the case n is 1, so there's one person with £2 to start with, and there's m plus 1 people, because there are m with £1, m plus 1 is the total. Now, with a person with if a person with £1 turns up, that happens with probability m, because there are m people with £1 over m plus 1. Right? Now, we've just said that we can't do this branch here. We can't serve this customer if they turn up first. But as soon as we serve this customer, we know we're good, because we have £1 change, and even if this person turns up next, we have £1 change for them. So this is fine. So the probability that we can do this is just this, right? It's just a single branch of a tree, so it's just this from here. So the probability is m over n plus 1. So that's the most basic case. The next case they ask you to talk about is what happens if there are two people with £2 coins. Now, this ends up being a little bit complicated. They give you a hint, which is to consider the first three people in the queue. But yeah, so let's say there are n, two people with £2 coins, and there are m, and now m is greater than 2. Now, the reason they're stressing that m is greater than or equal to 2 is because if m was only 1, then you couldn't do this, right? And the reason you couldn't do that is because you need 2 single £1 coins to serve 2 customers with a £2 coin, because you need £1 coin each to give them as change. So you're going to need to somehow get your hands on 2 single £1 coins. And since you don't have any coins to start with, the only way to do that is to get it from these people. So that means this has to be greater or equal to 2. Now, if we consider, I'm going to call, from this point onwards, I'm going to call people with £2 coins A, red A's, and people with £1 coins blue B's, and hopefully you'll see what I'm talking about there. Now let's think about some possible orders of these first 3 people, of these first 3 customers. Now, we've already gone through in the first example the case that if someone with a £2 coin turns up first in the queue, we can't do anything. We don't have any pounds, we didn't start with any money, we haven't got any money for anyone, so we can't do this. So we have to start with a B. We have to start with a blue B. Now again, blue B's were £1 customers, so we have to start with one of them. Now, if the second customer turns up as an A, if they turn up with a £2 coin, we're fine, because we have this person's £1 coin to give them, right? Now, we've taken a £2 coin from this person, but actually, if the next customer is an A, another £2-pounder, the £2 coin that we've taken this person is useless, because we need a single £1 coin to give to this person as change. So this doesn't work. Think it through. You get given £1. You give that £1 back to this person in exchange for their £2. But now when this person turns up with £2, you've got no actual change to give them, because you can't do anything with your £2 coin that you've got, right? You need a single £1 coin to give this person. So this doesn't work, right? We don't have any change for this person. So what we have to do is we have to start with a B. Then we can do an A. This is fine as long as a B turns up next, because we need that new single £1 coin before the next A turns up. And whenever the next A turns up, that's fine. If we start with this, we're good, because we have this single £1 coin now from this person. This isn't the only way you could do it, though. You could start with a B and then just have another B. Right? Now you've got 2 single £1 coins from these 2 people, which means whenever the A's turn up, you've got this reserve of £2 single coins built up, which means you can just give it to the A's whenever they turn up. So you're fine, right? So these are the 2 routes we can have. We can go B, A, B, so £1, £2, £1, or we can go £1, £1. Those are our 2 routes. So we can use a tree on that, right? So if the first comes up, we've got an A or a B. If they're an A, that's probability 2 over m plus 2. because there are 2 A's and there are M plus 2 total people. But that's kind of irrelevant because we can't continue from there anyway. We already discussed we need a B first. Now, the probability of a B is M over M plus 2, which is fine. And now we need to get to the next bit because we can actually have either choice here. There are acceptable routes for either. If another B turns up or if another A turns up, we can continue. Now, the likelihood of another B turning up is M minus 1, because be careful here, it's like GCSE probability without replacement. You've got 1 less M here because you've already seen 1 B customer, and you've got 1 less customer in total. And likewise here, you've still got 2 A customers in the queue, but you've got 1 less customer in total, so this drops down because you've already seen a B. And now from here, this is fine. 2 B's in a row already is fine. But from here, you need to make another branch with A's or B's on it. And again, be careful with these probabilities. The B is an M minus 1 now because on this kind of timeline, you've seen 1 B customer. So there's M minus 1 left. And now there's only M total customers left because M plus 1 drops, M plus 2 drops to M plus 1, which drops to M. And here, you've already seen an A, so that drops to a 1. And again, you have M total customers. But that's kind of irrelevant because we can't do BAA. But we can do this one. So therefore, we have either this route, which we multiply to find the answer to, or we have this route, which again, we multiply to find the answer to. So we're just doing this times this, which is these 2, plus this times this times this, which is those 3. And we just need to work this out, right? Now, I've highlighted these M's because, as you can see, what I can do here is I can just cancel them down. Now, I'm going to do this in a couple of different ways. See if you can spot what I've done to the 2 blue terms here. So I've cancelled out the M's and replaced them with 1s. That's always a good idea. But with these 2 blue terms, what I've done is I've just swapped them over. And there's a very specific reason that I've swapped those over. And it's to do with the fact that when you multiply fractions, all you're doing is multiplying the top and bottom. And multiplication is something that we can do in any order that we want. So I'm allowed to just swap those 2 over because 1 times 2 times M minus 1 is the same as 1 times 2 times M minus 1. So I'm allowed to just swap those over. And the reason I've done that is because now I can see, well, here and here, those 2 terms there that I've highlighted red, those are the same. Which means I can actually factorize those out. Now, you're used to factorizing, but you haven't quite seen it like this. But what I'm saying is, here's my first term, here's my second term. If I factorize out that red term, I'm just leaving behind this and then leaving behind those 2. And if I expand this out, you can see that this is going to be the same, right? If I expand this out, I'm going to have this times this, which is there, and this red times these 2, which is there. So I can factorize out that red one. This is cool because now I can sort this out. Obviously, this is just 2 over M plus 2, common denominator time. So I just add the numerators and you can see what's about to happen here. M plus 2 over M plus 2, cancel those all out, and I'm left with the thing that they asked me for. So that's quite a cute way of doing that. There are other ways you could do it. I mean, there are tons of other ways you could do it. So I'll just show you another one really quickly. So start at the same point, cancel those M's again, always a good idea. In fact, you could not cancel those M's and just factorize out that first term there, just like I did. And that's fine, but canceling the M's is probably a good idea. Next, what I'm going to do is I'm sort of just going to multiply each term together. Except I'm not really. I'm just going to sort of pretend like I'm about to. So these multiplied is this, and these 3 multiplied is actually just this. And why I've done this, and likewise, I haven't really expanded these or these, but why I've done this is because I now notice, well, this is just a common denominator, right? So I just add the numerators, and I can also expand those out now. So m squared minus m, 2m minus 2. And this simplifies, of course, add those together to make plus m, and then this factorizes quite nicely into that. I think, check my maths, but I think it factorizes, and now I cancel those and I end up with the same answer. All right, so loads of ways to do that, but it's really a skill worth having to be able to play around with these kind of things and get to the answer nice and easily. So yeah, take your time over stuff like that. Now, the bulk of this question is part 3. Show the probability when you have 3 people with £2 coins is this. Now, we're gonna have to be more careful here, I think. Now, we can't serve any of the A's if they arrive first. We need a B customer first, just like in the first 2 examples. But additionally, we need 2 B customers before we serve the second A, just like we saw in the example just before. We needed 2 of those Bs before the second A came along. Otherwise, we don't have those 2 single pound coins to give them. But now this is extended, right? Because now you need 3 B customers before the third A comes along as well. So this is going to get quite complicated, but let's think about some orders, again, with the first B customers. Now, if an A turns up, we're done. We've discussed this before. We don't have any money. So we need a B to turn up first. We can follow that with an A, that's fine, but we can't follow that with another A. And we saw that in the second example as well. We discussed that example as well. We don't have a single pound coin to give this person as change. So we need to start with a B. We can do an A as long as another B turns up. But we're not done here, right? Because there are still 2 A customers waiting in the queue. So if the fourth person is A, this is actually okay, because you have a pound from this person, give it to this person, but then you take in another pound from this person, a single pound coin, which you can then give to this person as change. But then if the fifth customer turns up, remember there are 3 A's in this queue. If the fifth customer turns up and is an A, now you're done. Like, you were so close, but you're out, right? Because you're only taking in 2 single pound coins. And this is what I was talking about. You need those 3 B's before the A's come along, all of them. But there's still promise here, right? You can go B, then an A. That's fine. You've given this person's pound coin. Then you go with another B. And now you can have an A next as long as there's a B last. Because now you have this person's single pound coin, which means whenever the A turns up after this, you have that person's coin to give them. So this is okay. But of course, there are other ways to be okay, right? You can do B, A, B, and then this B customer can just turn up a bit earlier. And now you're fine, because now you have a bank of 2 single pound coins in reserve, which means whenever the other 2 A's turn up, you can give them each those coins. So this is fine, right? And now what else is fine? Well, I've tested, it seems like, all of the A's here. So let's just start with 2 B's. And again, displaying systematic thought like this not only earns you marks, but also makes it less likely that you'll make mistakes or miss cases. We saw this in like assignment number, I think it was assignment number 6 or so, when we were finding all the digits that sum to 39 or whatever. Systematic thinking is going to help you out massively in STEP. So let's change that. We start with 2 B's. Now it feels like this is good, right? We've got a bank, right? We've got 2 single pound coins. Amazing. We're rolling in it. But then what happens if A? This is bad. We can't do this. We can just about get away with these 2. We give these 2 each of these coins, but this person turns up and we're done. So we can't do that. So we started really well, but we still can't do it. But we can do 2 B's, A, and then we can get away with a B turning up, because now we have this person's coin. So we're good. And likewise, this B can turn up a bit earlier if we want to. That's fine as well. So B, then an A turns up, then you have the B. This is okay, because now you've got those 3 single pound coins. So essentially, whenever the A turns up, you're good. And lastly, you could just go B. And now you've got 3 single pound coins, which means whenever the 3 A's turn up, you can just give them those coins. Right? So let's look at all the situations which are good. This one is good, this one is good, and this one is good. Those are my situations that are good. So now let's you'll appreciate that me drawing a tree for this would be very difficult. A 5-branch tree with this many cases is going to be enormous. So what I'm going to do instead is I'm just going to ignore the tree and just do each case like a table. So what's the probability of a B customer turning up first? Well, there are M B customers and M plus 3 total people to start, because there's 3 A's or 3 whatever, and M B's. So it's going to be M over 3 plus M, or M plus 3. Now an A turns up, there are 3 A's, remember? So that's going to be 3 over M plus 2, because there's 1 fewer person in the queue now. Next one, now there was 1 fewer M, so that's going to be M minus 1, because I've already seen one of them. And again, the number of people in the queue is going to shrink by 1 as well. Next A turns up, now there are only 2 A's left, right? Because I've already used 1. So it's going to be 2, and then this shrinks by 1 to get 2 over M. And then lastly, this number shrinks by 1 again to get to M minus 2. This number shrinks by 1 again to get to M minus 1. So notice how the total number of the people in the queue reduces by 1 every time. And the B's reduce by 1 each time, and the A's reduce by 1 each time. All right. And now what about here? Well, this is obviously the same as this. This is the same as this, because it's the same kind of case. This is the same as this. But now it changes, right? Because now we have M minus 2 B's left with an M left over. And I'm just going to fill this in quite quickly. And notice the pattern here. And again, this is why you want to set out your works really neatly with some real thought behind it. Because look how easy it is for me to spot mistakes in my working here if I've laid it out like this. All of these denominators need to be m plus 3s. All of these need to be m plus 2s. All of these denominators need to be m plus 1s, and so on. And likewise, I can easily check, do my b's decrease by 1 every time I see a b? Yeah, it looks like they do. Do my a's decrease by 1 every time I see an a? Looks like they do. Right? So being neat, being systematic about it is really going to save you a lot of stress and make it less likely to make mistakes. Now, at this point, I can throw away all context for this question. At this point, this is just pure algebra. What I need to do is I need to imagine this as a probability tree and multiply along all of my branches and then add up all of the cases that I have. So I need to multiply along all those branches and then add up all the cases. So I can ignore any context that this question used to have. This is just me doing some algebra now. All right. So instead of writing times, I'm going to use brackets. So I've just taken all of these terms and I've just put them all in brackets just so that I can see them easier. So I hope you're okay with that. I've just replaced all these times with brackets. I promise you this is all the same. You don't have to check it. It is the same as what appears down here via each row. So my objective here is to multiply all of these and add them all together. Now you can see here, I do not want to expand any of this. If I expand this denominator, I'm going to end up with what's called a quintic, an m to the power 5 term or polynomial. I do not want that. I don't want a cubic on the top either, which is what I'm going to get if I multiply all this together. Because if I end up with quintics and cubics, notice the answer. It's a beautiful, it's cancelled out, nice answer. If I end up with a quintic, I can't factorize quintics. I can't factorize cubics. You know, if I have a headache, I can barely do quadratics. So I'm not going to expand any of this, right? I'm going to have to be much sneakier than that. And now what I'm going to do is I'm going to firstly highlight everything in each row that has a matching numerator-denominator pair. So this m matches with that m, this m minus 1 matches with that. Again, this m matches with that, this m matches with that, and so on. And I can cancel all those out. So I'm just going to replace all those with 1s. The reason it goes to 1, of course, is because this is m times 1. So when you cancel, you're just left with the 1. So I'm going to cancel those all down to 1s. And this is looking better already, because now I don't have any quintics possible. I have some cubics still that would happen if I expanded out, which I'm not happy about, but that's okay. What I'm going to do is I'm sort of going to pretend like I'm about to multiply these out. So remember, to multiply fractions, you just multiply along the top and the bottom. I'm going to pretend like I'm doing that. So multiplying along this top is, well, I'm actually going to do 3 times 2 is 6, but then I'm going to leave the m plus minus 2 here. And likewise, I'm not actually going to multiply these bottoms out. I'm just going to pretend like I'm going to. Of course, the 1s don't mean anything in multiplication. So I'm just going to pretend like I'm going to multiply these out here. And what I've noticed, and I've done that every time, 3 times this, not expanded it. 3 times 2 is 6 times this, not expanded it, and so on. And the reason I've done this is because I've noticed, look at these denominators. It's common denominator time, right? Amazing. So I can add all these fractions together because I can just leave the denominators as they are and just add all the numerators. And now also notice, well, I've got 6, when I'm adding these numerators together, I've got 6 m minus 2's here and another 6 m minus 2's here. So on the top, that's going to make 12 m minus 2's. And here I've got 3 m minus 1 m minus 2's. And I've got another 3 m minus 1 m minus 2's here. So that's going to make 6 of them. And then here I've got this cubic here that I don't really like. And now, again, I'm not going to expand the bottom because I don't want cubics. I really don't. So I don't want to expand this either because that's going to give me a cubic, right? There's an m cubed term here. So I really don't want that. I can't cancel anything because I can't see any terms that are the same as these up here. But what can I see? Well, look back at the question. Here's an m minus 2. Where's the m minus 2 coming from on this top? Well, I can actually see it, right? There's 1, there's 1, there's 1. So if I highlight all of those red, I'm going to highlight the m minus 2's red. I think I can factorize those out. I think I can factorize those red m minus 2's out and leave behind a 12, a 6m minus 1, and an m minus 1, right? Because this is just a triple term here. I can factorize that m minus 2 out. Okay, well now look at the blue bit. this is finally a quadratic, like, because the highest thing it's going to give me is an m squared, and I'm okay with that. I can deal with quadratics. So let's just expand this finally. Let's actually deal with this. That's going to make 12 plus 6m minus 6 plus m squared minus m. And now let's simplify and rearrange this a little bit. I get m squared plus 5m from those two plus 6. And if this moment doesn't give you pure joy, then maths has nothing to offer you as a subject. Like, you should be, well, you should be, but like, you're barking up the wrong tree with STEP if you don't even slightly smile inside seeing this, because look at this blue term. That's clearly m plus 3, m plus 2. And then, of course, I cancel down, and I'm left with m minus 2, m plus 1 as required. So yeah, a really great question.